Hey, how's everyone doing today? How was your Easter weekend? I was also fine. It was very nice. Oh, did I not post the lecture? Wait, the exam grades taken back down? Were they? Let me check. Okay then. I was under the impression. Okay. I guess the course coordinator did that manually. I was under the impression that we could let y'all see the grades at least, but not reveal the like not show the upload one where we show the grading and you see what you got wrong until everyone's taken the makeup exams. Yeah, I thought we were able to show the grades in particular because next week is the end of next week is the last day to or at the end of this week is the last chance you have to drop the class. I guess I was mistaken. I think he went through when he was looking at the averages and hid those. So that is my fault. I did not realize that. Other classes already have comments? What? Dude, okay, I don't know then. It was clearly I'm pretty sure he manually went in and hit it. So yeah, let me see if I got an email on this. Okay. Wait. Oh, okay. So a couple days ago, I got okay. Okay. Yeah. Yep. That was my bad. Okay. I will release those again. Sorry about that. All right. Good stuff. Okay. Yeah, so I mean there is likely to be some kind of curve at the end, but like I said before, it's it's not a very visible curve. As a student, you're not going to be able to immediately see, okay, this grade has been curved, so I'm doing this well. The way the curves work is the cutoffs at the end for the grade cutoffs for A, B, C, etc. Are adjusted at the end. All the exam grades stay the same. It's just if the exams were particularly bad in some spot, then maybe we'll adjust the cutoffs down. But the thing is, you guys are not able to see exactly what those cutoffs are. So yeah, it's not the most convenient thing from the student standpoint. But there usually is a bit of a curve if the grades are particularly bad on an exam. You just might not be able to see exactly what it is. But I wouldn't expect an enormous curve. Yeah. No, we're not supposed to say. For the simple reason that one person finds out, everyone finds out. and then every person that's within, 1 point of a cutoff or something in, some far-flung section will spam their professor with requests to be bumped up. And so for that reason, we have a code of silence on the cutoffs. We're not supposed to tell anyone what the cutoffs are. Yeah. What was the exam average overall? Over all the, looks like over all sections and all exams, it was 75. Yeah. But yeah, I will re-release the grades right after lecture. I want to get started on lecture. Okay. All right. So today we are going to start looking at line integrals. Okay. In the interest of time, I'm not going to go through the derivation of all this because if you want to see it, you can look in the book, you can look on Wikipedia, you can look in any number of places. And I don't think this usually sticks with most students. So we're just gonna look at what a line integral is and how do we compute it. So suppose we have a curve. So this works for curves in R2 and curves in R3, but suppose we have a curve in R3. Suppose our curve is in R3. So we have a curve C. So then we can integrate a function along this curve. So it's a single integral in this case. So we have a function of 3 variables. So we'll see later. We can think of this as there are like several physical things we'll often use that will integrate along line integrals. Sorry, so we're going to start off looking at how to integrate scalar functions. So we'll look at scalar line integrals. So we have a function defined in R3, and we have some curve. So we can think of the function, for instance, as giving like density. Suppose this is like a wire that we've twisted and whatever, and it lies in space. And we can look at the mass density, say, along that wire. So if we want to find the total mass, the way we did it before is we integrated, if we have a thin flat plate, for instance, in R2, we would integrate the density over the region, over the plate, and that would be the total mass. The same thing works here. If we want to find, say, the total mass, and f of x, y, z gives us the density along the wire, then we integrate along the curve. So we integrate along C, the function f of x, y, z, with respect to arc length, ds. So S is going to be arc length like it was before. So now we have a function of 3 variables because we're in R3, right? And we define a function of 3 variables on R3, but it's a single integral because we're integrating along a one-dimensional object, along a curve. And we're integrating with respect to arc length in this case. So don't let that confuse you too much. Okay. All right, so how do we compute this? So this is the thing this is the integral we're computing. How do we compute it? What we do is we parameterize our curve. Often you're given a parameterization, but sometimes you need to parameterize it yourself. So we parameterize our curve C. So we use a vector function, R of t. Oops. So remember back to vector functions. R of t is going to be x of t, z of t, y of t. And we let t go from A to B. So remember, when you parameterize a curve using a vector function, what we're doing is we're thinking of vectors starting at the origin. So a vector valued function, vector starting at the origin with the endpoint, the tail, or sorry, the tip of the vector tracing out the curve as t goes from A to B. So say we start out here at time A. So this is R of A right here. We end here at time B, and at some time t in between, we're at some point along here. And as t varies from A to B, we're tracing out this curve. So let's say we're moving along this direction along the curve. So either you're given a parameterization or you need to parameterize your curve. Then we replace x, y, and z in the function we're integrating. So we replace x, y, and z in the integrand, the thing we're integrating, f of x, y, z, with their parameterizations. So we replace x with its parameterization in terms of t, y with its parameterization in terms of t, z with its parameterization in terms of t. And for shorthand, we will write this as f of R of t. So keep in mind, this doesn't literally make sense, this f of R of t, because f is a function of 3 variables. You're plugging in a point, x, y, z, from R3. Here, this is saying we're plugging in a vector, x of t, y of t, z of t, into the function, which doesn't literally make sense, but it's a convenient shorthand. And that stands for the point x of t, y of t, z of t, rather than the vector. But it's a nice shorthand that we're going to use. Any confusion on that point, right? We're just replacing x, y, and z with their parameterizations. Okay, so we parameterize, replace in the function that we're integrating x, y, and z with the parameterizations. And then we let ds becomes, just like before, magnitude r prime t dt. Remember, we thought of ds recall before ds dt was speed, which is our magnitude r prime t dt. Oops. So just think of multiplying by dt. There. So ds is magnitude r prime t dt. And then we put it all together, integrate from a to b. So we have the integral over c over the curve c of the function f of x, y, z with respect to arc length is, if we parameterize c by the vector function r of t, t goes from a to b, it's the integral from a to b of, you replace x, y, and z with their parameterizations in the function, and then ds becomes magnitude r prime t dt. So you need to multiply the function where you place x, y, and z with their parameterizations by the magnitude r prime t. And then we integrate from t equals a to b. Okay, so this is where c is parameterized by r of t, t goes from a to b. Okay, so let's do some examples. And also let me say, this is a good thing to remember. So often it's not the easiest thing in the world to explain physically what a line integral of a scalar, what a scalar line integral is. But arc length is pretty easy. So arc length we can think of. So arc length of your curve C is going to be the integral over C of 1, the function 1 with respect to arc length. So that works just like if you want to find the area of a region in R2, you integrate 1 over that region with respect to area. If you want to find the volume of a solid region in R3, you integrate 1 over that region with respect to volume. If you want to find arc length of a curve, you integrate 1 over that curve with respect to arc length. That's good to remember. And we've already seen this, remember. That's just the integral from a to b magnitude r prime t dt. We've already seen that formula for arc length. But if you use the thing directly above it, those are the same thing. That's how we evaluate the integral of 1 with respect to arc length. Okay. Let's do some examples. So let's evaluate the integral over the curve C of the function x plus y plus z with respect to arc length. And here C is going to be the helix, which is given by or parameterized by r of t is cos t, sine t, t. And then t is going to go from 0 to 3 pi. Okay. So we already have a parameterization, so that part's taken care of it for us. So what we need is we're going to replace x, y, and z with the parameterizations, and then we're going to need to change ds to magnitude r prime t dt. So let's calculate magnitude r prime t. Okay. So magnitude r prime t. So we take r prime t. We just take the derivative of each component. So derivative component by component. Cos t goes to negative sine t. Sine t goes to cos t. And t goes to 1. And we take the magnitude. So what's the magnitude? It's the square root of the sum of the components squared. What is the magnitude of negative sine t cos t1?
Is it square root of 2?
Right. So we have a sine squared plus cos squared, which is 1, plus 1 squared, which is 1. So square root 1 plus 1 is root 2. And that's magnitude r prime t. So particularly simple in this case. It's nice. Okay. So we have everything we need. Okay. So we're integrating t from 0 to 3 pi. We replace x, y, and z with the parameterizations. So remember, with the parameterization, the first component tells you what x is. The second tells you what y is. The third tells you what z is. So the first component's x of t, the second's y of t, the third is z of t. So x plus y plus z becomes, well, x we're replacing with cos t. Y we're replacing with sine t. And z we're replacing with t. Let me just emphasize that. And ds becomes magnitude r prime t dt. Well, magnitude r prime t is root 2. And so this is relatively simple integral here. Okay, so cos t, when we integrate, becomes sine t. Let me pull this root 2 out, because everything's being multiplied by root 2. We can't forget about the root 2. Sine t, when we integrate, becomes negative cos t. And t becomes t squared over 2. And we're evaluating from t equals 0 up to 3 pi. Okay, sine t at 3 pi and 0 is 0. Minus cos of 3 pi minus cos of 0. So that's negative 1, negative, negative 1, minus 1. So that is 2. And then the t squared over 2 evaluated at 3 pi is going to be 9 pi squared over 2. Oh my goodness, dude. And that is our final answer. Yeah, yeah. So what we did is we just turned it into a math 140 integral, right? We turned it into a single integral of a function of one variable, right? So we started off with a function of 3 variables, but we wrote each of those variables in terms of a single variable t by parameterizing. And then in the end, we just end up with a math 140 integral, a function of one variable, which you should all be very familiar with picking. Okay, so you parameterize, that's already done for us. You replace x, y, and z with the parameterizations. ds becomes magnitude r prime t dt, and you integrate from a to b. Pretty straightforward. You just need to remember, basically, the ds is magnitude r prime t dt. Okay. So for that same curve, C, let's find the arc length real quick.
So for that last example, did we just find the parameterization, or like what would this be?
It was given to us. Yeah. In this case, it's often going to be given to you, unless except for rather simple things. We'll do an example in just a sec where we need to find the parameterization.
Okay.
Often it's just given to you. Yeah. Yeah, it's typically only going to be very simple things. Okay, what is the length of the helix C? From the previous example. So we want to find the arc length. So remember, so C was given by cos t sine tt, and t goes from 0 to 3 pi. So remember, the length of a curve is just the integral over that curve of 1 with respect to arc length. So we've already done all the work here. We found magnitude r prime t, et cetera, et cetera. So we integrate t from 0 to 3 pi. We go to our function that we're integrating 1, replace x, y, and z with the parameterizations. Well, it's just a constant, so that's still just 1. And ds becomes magnitude r prime t dt. And we said Magnitude r prime t was just root 2. Oh, not square root r prime. So we're just integrating root 2 from 0 to 3 pi. And that is, of course, just oh, 3 pi root 2. So, yeah. Okay. Any questions?
Wait, I'm sorry. Quick question. So
Uh-huh.
is this like, were you using the same integral for this, but you just kind of like changed the problem a little bit, or?
Oh no, so it was the same curve we're integrating, but we're just integrating a different function, right? So we wanted to find the length. So we integrate 1 with respect to arc length. So what we go to our function that we're integrating, you replace x, y, and z with the parameterizations. Well, it's a constant. There is no x, y, and z, so that remains 1. And then ds becomes magnitude r prime t dt. And we already calculated the magnitude r prime t. That was the root 2 from before. And so this just becomes the integral of root 2 from 0 to 3 pi, which is a very easy integral to evaluate.
Right. Yeah. I just saw something change. Just want to make sure. Thank you.
Okay. Yeah. Okay. So I mentioned before, we can use scalar line integrals to calculate the total mass of a wire, for instance, if we're given the density, the mass density along the wire as a function. Cool. So we're given the density. So the mass density along a wire is given by delta. Actually, I think they use rho now, just to be super confusing. But that's our density function. So along a wire C. Then the total mass, the mass of C, is of course just the integral along the curve C, along the wire C, of the density with respect to arc length. And this works perfectly fine if we're in R2 also and the density is given by a function of 2 variables. Arc length, line integrals we can also compute in R2. As we'll see in the example we'll do in just a second. And the way we calculate it works exactly the same way. We parameterize now by a vector function, but it's going to be a 2-dimensional vector, x of t, y of t. And then you just replace ds with magnitude r prime t dt. It works out exactly the same way. But yeah, if we're given the density of our wire, if we want to find the mass, we integrate the density along the wire. And since it's just a curve, it's a 1-dimensional object, we're just doing a line integral along it. Let me do this on the next page. Same thing if we're given like charge density. And if you want to find total charge, you integrate the charge density along there. So let's find the mass of the wire, which is bent in the shape of the parabola y equals x squared. So we're in R2 now. So we're just bending this wire in the plane in the shape of the parabola y equals x squared, where x is going to go from 1 to 4. Oops. And here our mass density is going to be y over x. Grams per centimeter. And let's suppose our units are centimeters in the plane. Okay, so we have our curve C. We need to parameterize it. We're not given a parameterization. And we're given the density. We need to find the total mass. Okay, so first thing we need to do is we need to parameterize our curve. So we got to parameterize C. Okay. So there are lots of different ways to parameterize. There are infinitely many ways to parameterize your curve. The easiest way in this case, so we know it's all the points on this curve are going to satisfy y is equal to x squared. Right? So this is really nice because we have one of the variables written in terms of the other variable. We have one of the variables by itself, y, and we've written it in terms of x. So we have y by itself. So we're going to let the complicated variable, right, the one not by itself, in other words, x, we're just going to let that be t. So we're going to say x is t. And if x is t, then y has to be equal to x squared, which is t squared. Does everyone understand that bit? Okay. So there are two important pieces of parameterization, right? There is, you have to write x, y, and z in terms of t. But the other piece is we need to figure out what the range of t is. Otherwise, we can't integrate because we wouldn't know what to integrate to and from. So we're told in the parabola y equals x squared, x goes from 1 to 4. Well, x is t, so t goes from 1 to 4. Pretty simple. So if we were just told we go from like the point 1, 1 to the point 416, then you would have to say, okay, the points are t squared. So the first coordinate gives us t. So we're going from t equals 1 up to t equals 4. There are different ways we could do this, but this is our parameterization. Okay, so we have our parameterization. Now we need to find magnitude r prime t. Oops. So r prime t, r of t is t squared, r prime t, we take derivative component by component, so that's 1, 2t. So what's the magnitude of r prime t? No, t is, no. So we have the curve y equals x squared. So if we're in R2, there are only two variables. We get one of the variables. If you can get one of the variables by itself, in this case, y, we let the complicated variable, the x squared, the x, be t. And then when you plug in that variable's t, that tells you what the other variable has to be that we have by itself. So if we let x be t, then y is equal to t squared. And so we get x is t, y is t squared in this case. And that's our parameterization. Does that make sense?
Yeah, I was just thinking, right, if we assumed x is equal to t and we plugged that into the y is equal to x squared and we took the square root to find what y was equal to.
Well, why are we taking the square root? Because we know x is t, and we want to find out what y is.
Okay,
Well,
right, so then it would be t squared. Yep.
Exactly.
Okay.
Yes. Yeah. Okay, so r prime t is 1, 2t. So the magnitude of that is the square root of 1 squared, which is 1, plus quantity 2t quantity squared, which is 4t squared. Okay, so let me calculate our integral. So we know the mass is equal to the integral over our curve C of the density y over x with respect to arc length. And so plugging in what we just calculated, we know t goes from 1 to 4. What is y over x when we replace x and y with their parameterizations?
T.
It's just t, right? T squared over t. And we said ds becomes magnitude r prime t dt. So that is square root 1 plus 4t squared dt. So this t is our y over x. And this whole bit is our ds, our magnitude r prime t dt. And this is a 140 integration. We just use sub. So let u be 1 plus 4t squared. du is going to be 8t dt. So we have t dt, so we have 1 over 8 du. So square root u is going to go to 2/3 u to the 3 halves. So 2/3 1 plus 4t squared to the 3 halves. And we're evaluating that from t equals 1 up to 4. And when we do that, we get 1/12. So 4 times 4 squared is 64. 65 to the 3 halves. Minus 1 plus 4 times 1 squared, which is 5. To the 3 halves. We get 1/12 of that. We just do a simple use up there. Okay. Last slide for a second. Okay. It's the same thing. The total, whatever, if you have a density, charge density, population density, mass density. If you want to find the total, you integrate the density. Yeah. But if you're integrating along a curve, then it's a line integral in this case. Okay. Any questions about scalar line integrals? Okay. So next class, we're going to look at how to integrate vector fields over curves and how that relates to the concept of work in physics. Yeah. All right. So I'm going to move over to the office hours Zoom if you have some questions, and I will unhide the exams again. And have a great rest of your day. And I will see y'all on, so Wednesday is a wellness day. So I won't see you guys until Thursday. So have a nice couple days off, and I will see y'all later.